Hello everyone. Today in this video I want to create a new project in order to show you if you want to have both CPU0 and CPU1 of a Zinc SoC device work together as an AMP architecture. What are the steps to start the project and complete it in this regard? First of all, as like other project, I will go to create project. I will choose next, and then I will choose a name for the project. And the destination. The next. There is no need for specifying the sources at this time. The target word for our project is Zybo, so I will search it here and then choose it here from the menu and then next, and then finally finish. As the first step, I will create a block design. You could change the name, but there is no need. In the created block design, I will complete the design in this regard. First of all, I'm going to add IP, and the first IP that I'm going to add here is the Zinc processing system. Two key features of these examples are as follows. We have two CPU. The CPU0 is responsible for observing the key press from the PS side and then control the LED on the PS, again on the PS side, and then generating a software interrupt to the CPU1 and wake it up. And also CPU1 is also responsible for detecting the pressing of the key from the PL side and controlling again the LED from the PL side. So in order to reading the key from the PL side and again writing the data on the LED again from the PL side, I need two Xi GPIO block. So in this regard, I will add these two blocks or these two IPs. This is the first one. I will go to the IP configuration and then I will choose all output and the width to 1. Here I could enable dual channel and use the second channel of this Xi GPIO IP as all inputs for connecting to the key. But for the clarification, I'm using two Xi GPIO IPs and then one for the key and another for the LED. Okay, the next Xi GPIO. This one is for the key, and I will choose this width as 1, and I will also enable the interrupt. Okay, we'll go to run block automation, and this block of automation option is just for Zinc processing system. I will choose OK. Okay, I have to double click on this Zinc PS block and enable the interrupt. Fabric interrupt. And this one. And then I will choose OK. Okay, as you could see, the interrupt is enabled here. I will connect it to the interrupt of the Xi GPIO1 and then go to run connection automation in this regard, because as I told you, this Xi GPIO is for connecting to the LED. I will choose LED for buttons. On the Zybo, we have 4 LEDs, And if you go also to the second GPIO here, you could see that we also have 4 buttons. So the width that I change it to 1 in the configuration doesn't have effect on the final result. The result of the number of feeds that will be generated here is totally dependent on the change or setting that you apply in the run connection automation. Okay, if I choose OK, we will see that the block design of this project will be completed like this. By using this option, I could modify it in order to be more clarified. As you could see, the XI GPIO0 is for LEDs. I couldn't change the bits to 1 because by default, because of the Zybo board and the number of LEDs that are available on that board. And there are 4 bits LED and also 4 bits buttons. And then the interrupt, as you could see, is connected to the interrupt of the Zinc processing system, and 2 other IPs have been added to the design automatically: the processor system reset and the XI interconnect. So the design is complete now. In the next step, I have to go to the source tab here and right click on this block design that we already generated here, and then choose create a wrapper. By this, the top module Verilog code is generated here. In the next step, I will go down in the Flow Navigator bar and then go to Generate Bit Stream. By doing this step, all the run implementation and run synthesis will be automatically done, and then the synthesis and implementation result will be completed. Okay, it takes some seconds, so I will pause the video and I will be back again. After bit stream generation successfully completed, and it is written here that write bit stream complete, go to the file and then choose export hardware, and then check include bit stream, then OK. Again, file, launch SDK. The SDK tool will be open after that. In SDK, I have to generate for 2 board support package and 2 application project for each of the CPUs. First of all, I will go to File, New, and I will choose board support package for the CPU0. Here I have to choose a name for that. I will choose CPU0 board support package BSP, and then here I have to choose Cortex A9 0 because we want to have a bare metal application. Standalone will be chosen, and then finish. Here in this page there is no need for applying any other changes, so I just confirm this page, and the board support package is generated. After build finished, I will go to the file, and then this time I will choose new application project. I will name it as CPU0. Okay, and here I have to change it to use existing CPU0 board support package. This the board support package that I already generated here. And then I will confirm this page and go to the next. Here it will ask me if I want to use different templates. For example, hello world is a special template that at the start somebody use it, but here I'm gonna choose empty application and then finish. Then I will go and generate a new board support package, this time for CPU1. So I will name it CPU1 BSP, and I will choose Cortex A9-1 this time, again a standalone, finish. In the pop-up window, I will go to PS7 Cortex A9-1, and then here in extra compiler flag, I have to add another flag here. Then here we have to add this, which is a compile time macro definition that will tell the CPU1 application that this project is being built for an asymmetric multiprocessing setup. After applying this change, I will confirm this one, and the second board support package will be generated, this time for the CPU1. After it becomes completed, I will again go to the file and then new. This time I will choose another application project. I will name it as CPU1. And also I have choose the second processor for this application project, and then use existing CPU1 board support package, the last board support package that I already generated. And then finally I select next and then choose the application and then finish. Next step, I will go to this CPU0 application project folder, and then on the src folder I will right click and choose source file, and I will generate main.c code, finish, and I will complete the code which is related to the CPU0 processor. As you could see, share.h is not recognized here. If I save it, some error related to this will be generated. So again, I will right click on that and choose new. This time I will choose the header file and I will generate share.h file. Okay, we will complete this share.h file. This code defines a new data type called share mem, and it is using a C struct. The structure contains two fields that are typically used for managing a shared memory region. Both lengths or addresses defined here. And then if you save it, you could see all the errors on main code will be disappeared. In the next step, I have to go and write the code for the CPU1. Again, choose src and then click on new and source file, main.c. Then I will complete the code for the main.c. I will share the GitHub link related to the different main and share.h files that are related to this project. So don't forget to read the description of this project. Okay, again, as you could see, I have error here on share.h because it's exactly the same as CPU0. Again, I will right click on this, and this time again I will choose header file and I name it share.h, finish. Again, I will complete it the same as what I did for CPU0. Okay, in the next step, I have to go to different linker file, which are, we could find them here. I have to choose the base address for CPU0 and also the size, because the DDR memory on the Zybo board has 512 memory size, so I will choose half of that, which is 256 or 55. Okay, so I have to choose this size which is related to this number. Okay, here I have to change it to 255 megabyte, and then if I come out from this, I have to save this with Ctrl S. Again, I will go to the same file which is related to CPU1 this time, and I will double click on that. The amount of base address should be out of the range of the CPU0. Okay, I have to save it again. After we finish doing all this setting, the next step is to connect the board to the PC. After connecting the Zybo board to the PC, you have to turn it on. Then you have to go to the run configuration and then double click on this system debugger. In the target setup, you have to choose the standalone application, and as you could see, all the setups has been completed here with the stream file and then initialization file, FPGA device auto detect, and the PS device. You should also check this reset entire system and then go to the application. Both of these should be checked because I want to use both CPUs. Then apply the setting and then run. After programming the board has been completed, then we will go and open the PuTTY. In PuTTY, I have to apply some changes. For example, the connection type is serial, and then I have to connect it to the equivalent serial port, and the speed should be this one. If you are not sure about the serial port, you should check it on the device in the device manager. And then if I check open, this page will be pop up, and then as you could see, if I press the key that are related to the PS, the CPU0 will work, and then type hello CPU1. This is CPU1 because it will generate a software interrupt to that CPU and it will wake it up. Again, if I press a key which is connected to the PL side, the LED of the board will be turned on, and also it will generate it hello CPU0. If I want to show you what I have done on the board, I have pressed this key for the key that is connected to the PL, and as you could see, this first LED has been turned on, and also for the PS side for CPU0, I have pressed this one, MIO CPU051, and then the equivalent LED, which is MIO7, will be turned on. Okay, if I want to summarize the content of this video, in this example we implement a dual processor AMP project. The two key features of this example are the CPU0 is responsible for detecting key press from the PS side and control the corresponding LED again on the PS side, and then send a software interrupt to the CPU1. After this interrupt has been received by CPU1, it will be allowed to print a string of character in its own memory space. The CPU1 is also responsible for detecting key press attached to the PL side. Once this key is activated by the CPU1, it controls the LED on the PL side and sends another interrupt to the CPU0. After receiving this interrupt, the CPU0 prints a string of characters in its memory, as you could see here in the result on the PuTTY. Okay, this video has been finished here. I will share you all the codes required for completing the project, the link that is related to that GitHub file.